Hi everyone, so I'm making the second video of mathematics exposition, and the first video was a peek into the world of probabilistic methods, and hopefully I helped usher you a little bit into this really intriguing world with lots of fascinating problems and lots of fascinating applications of probability in problems that a priori have nothing to do with probability. So I told you that I'm following this book, The Probabilistic Method, by Noga Lon and my own doctoral advisor, Joel Spencer. And I'm trying to follow the chronology the sequence that has been followed in the book. However, a lot of chapters in the book, or there are a lot of chapters in which a large portion is all about ad hoc examples and applications to ad hoc examples of some principle or another. And so, of course, it's not possible for me to go through every single example. That's something that I would leave to you if you are fascinated enough by this topic to sort of delve into. And this book is also available on the internet, I think, as an ebook. And I don't actually know how expensive the book, the hard copy of the book is if you live in India or the Indian subcontinent. But it should be available as an ebook, so you can look the examples up there. What I will do is I will move on to chapter 2, which is where we focus on linearity of expectations, and I'm going to try and show you a few examples of where this principle gets applied to, and then hopefully, as and when I have time to record the next videos, I would like to focus on such principles, like instead of focusing on lots and lots of applications. Applications are great, so we will do a few examples at a time, but I also need to sort of, if I'm doing a mathematics exposition video, I should also talk about the central principle, the central idea that is at play. So that's what I'm going to try and do, picking out topics from this book and trying to follow the order that the book has followed. Okay, so let me share my screen. And hoping this is visible, I'm going to go to full screen mode. And what is the central idea of linearity of expectations? Basically, you start with a finite collection of random variables. Let's call them x1 through xn. And let's say that expectation of xi is well defined for every I. So one sufficient condition of ensuring that is ensuring that expectation of the absolute value of xi is finite. So we are making no assumption whatsoever on the joint distribution of x1 through xn. They could be highly dependent, they could be highly correlated, they could be uncorrelated, they could be independent. All of these situations are possible. We make no assumptions. That's why it's written in italics, and then I have emphasized that they need not be independent. So we make no assumptions on their joint distribution. It can be anything, but when it comes to expectations, here's the nice consequence. It doesn't matter what their joint distribution is. The expectation of the sum of these random variables is always equal to the sum of their expectations. Okay, so expectation of summation I running from 1 through n xi is equal to summation I running from 1 through n expectation of xi. So you can interchange the order of expectation and summation here. And this is what is known as linearity of expectation. This is not true if you go over to second moments like variance or higher moments. There you end up getting a lot of cross terms. Like in case of variance, you get a lot of covariance terms. So you have to take care of those things. But in case of expectation, we are safe from that trouble. And this actually ends up making our lives really a lot simpler than they would have been otherwise in several applications, as we shall see. Another property that we're going to make use of while I illustrate the applications of this idea to the examples that follow is the following, that if x is a discrete random variable, we're going to focus on discrete random variables for the sake of this talk. So that's why I'm just focusing on discrete. And expectation of x is some real number mu, then x definitely assumes some value which is less than or equal to mu with positive probability, and some value which is greater than or equal to mu with positive probability. So Notice that we are not able to get rid of the equality in these inequalities. So these inequalities are not strict. If expectation of X were strictly less than mu, then you could say that capital X would assume a value which is strictly less than mu with positive probability. And if expectation of X were strictly greater than mu, then you would be able to claim that X assumes some value which is strictly bigger than mu with positive probability. Since here we just have equality, so we have to retain the equality in these inequalities as well. So now let's move on to the applications. The first one is on tournaments. What is a tournament? A tournament is a directed complete graph. Okay, why is it called a tournament? So let's look at this from the perspective of, let's say, soccer. Okay, I don't know if there are a lot of people from India who are watching this particular video, then you guys would probably prefer an example involving cricket, but I love soccer, so I'm going to illustrate it with soccer. So let's say that you have three teams, Real Madrid, Barcelona, and Valencia, okay, and they are playing each other. Okay, so each pair of teams plays a game against one another precisely once. Okay. So let's say Real Madrid and Barcelona play, and Barcelona defeats Real Madrid. Then Barcelona and Valencia play, and Barcelona again defeats Valencia. And finally, Real Madrid and Valencia play, and then Real Madrid defeats Valencia. How can you represent this via a graph? You can start with three vertices that you label as Real Madrid, Barcelona, and Valencia. And then you can put directed edges between every pair of vertices in this graph as follows. So you place an edge between Real Madrid and Barcelona, and then you add an arrow to indicate its direction that goes from Barcelona towards Real Madrid to indicate that Barcelona defeated Real Madrid. Okay. Then you place an edge between Barcelona and Valencia, and then again you direct that edge from Barcelona towards Valencia with an arrow to indicate that Barcelona defeated Valencia. And finally, you put an edge between Real Madrid and Valencia, and then you add a direction from Real Madrid towards Valencia using an arrow. This is what a tournament looks like. So it's a complete graph, but then there are directed edges. And in particular, you have to keep in mind that if X and Y are two labeled vertices inside this graph, then either you have the directed edge that goes from X towards Y, which is indicated by this notation. So open bracket X comma Y and close bracket, and the brackets I'm using are parentheses here to indicate that these are directed edges. Or you have a directed edge that goes from Y towards X, which is indicated by, of course, the reverse notation. But you cannot have both, okay? So it's like you're forcing these soccer games to end in a clear-cut decision, not in a draw, okay? So you let the soccer games carry on for extra time and penalty to make sure that one of the teams wins and the other one loses. No draw is allowed. Okay, so next we talk about Hamiltonian path, and probably most of you know or have heard of Hamiltonian paths and Hamiltonian circuits. We will focus on Hamiltonian paths here. So Hamiltonian paths can also be defined for undirected graphs, but for the sake of this particular scenario, we will talk about directed graphs. So let's consider a directed graph, capital G, with labeled vertices V1 through Vn. You say that a Hamiltonian path, you say that first of all, it has to exist. It may not exist in every graph. And if it exists, it will look as follows. You will have some permutation pi of 1 through n. So pi of 1 through pi of n is a permutation of 1 through n, such that when you consider the sequence of vertices v sub pi of 1 through v sub pi of n, then there is a directed edge that goes from v sub pi of 1 to v sub pi of 2. Then there is a directed edge that goes from v sub pi of 2 to v sub pi of 3, a directed edge that goes from v sub pi of 3 to v sub pi of 4, and so on until you get to v sub pi of n minus 1. And the directed edge must go from v sub pi of n minus 1 to v sub pi of n. So I wrote that here. The directed edges v sub pi of I towards v sub pi of I plus 1 have to be present for all I running from 1 through n minus 1. Okay, so basically, if you imagine yourself as a walker or an explorer, you start at v sub pi of 1 from, and also you have to obey the rule that when you're walking, when you are exploring the graph or walking on the graph, you have to follow direction, that is the directions that are specified by the directed edges. Okay, you cannot walk in the opposite direction to an edge. Okay, so you cannot violate the directions of the edges. So from v sub pi of 1, there will be a directed edge that can allow you to walk to v sub pi of 2. From v sub pi of 2, you can walk to v sub pi of 3 along a directed edge, and so on until v sub pi of n. And this way you are able to visit all the vertices following directed edges. Okay, so this is what a Hamiltonian path looks like. If it were a Hamiltonian circuit, then you would also require that there is an edge from v sub pi of n to v sub pi of 1, so that you can come back to your starting point, but that is not what we are looking at here. We're just looking at a path. Okay, so here's my claim, which we will prove using probabilistic methods in the next couple of slides. You can find a tournament with n players that contains at least n factorial times 2 to the power minus n plus 1 many Hamiltonian paths. Later on, we will see how large this number can be. But for now, let's just focus on the proof of this. Let me just mention here that when you use probabilistic methods, to the best of my knowledge, most of the time you are answering existential questions. You are answering a question as to whether something can happen or something cannot happen. Okay, but there is another aspect of this kind of problems, which is the algorithmic aspect, where you try to find out if you can actually perform an algorithm to construct such a tournament. Okay, so for example, in this particular problem, how easy is it to construct such a tournament? Okay, can you find a polynomial time algorithm to construct such a tournament? That sort of questions have a very different flavor, and as I say, to the best of my knowledge, probabilistic method does not actually aid you in coming up with algorithms like that. I mean, you can come up with random algorithms, but I don't think that comes under the purview of probabilistic methods. So we will just focus on proving that there exists such a tournament, and we will make use of probabilistic method for that. Okay, so I'm going to just pause this for a little bit. I'm just trying to find out how to do that. So I'll stop sharing, and I'm going to pause my recording just for a little bit because I just noticed a typo in my slides. I'll be back. Okay, so now let me share the screen again. And let me go to full screen. We will talk about the probabilistic method that we employ to establish our claim. So we'll start with n labeled vertices v1 through vn. And now we will set up a random tournament on these n vertices as follows. So for any pair of indices I and j, where I is not equal to j, so these are a couple of distinct indices, you either add the directed edge that goes from vi to vj with probability half, or you place the directed edge that goes from vj to vi, that is in the reverse order, with probability half. Okay, and you do this independently over all such pairs of vertices. Okay, so basically you're starting with n vertices. Between any two pair of vertices, you either place one directed edge with probability half or the opposite directed edge with probability half. So which one you're setting down is a random variable here. And you do this independently over all the edges, over all pairs of vertices of the graph. Okay, so this gives rise to a random tournament. Now, let's consider any particular permutation pi of 1 through n. What is the chance that the sequence of vertices defined by this partition will give you a Hamiltonian path? For this to happen, as we saw in the previous slide, this condition needs to be satisfied, which means that the edge that you have placed under the random tournament from between v sub pi of I and v sub pi of I plus 1 needs to go from v sub pi of I towards v sub pi of I plus 1, which happens with probability half. And this has to happen for every I running from 1 through n minus 1. We have already stated that in our random, in generating this random tournament, we added the directed edges independently over all pairs of distinct vertices. So therefore, the probability that there is a directed edge from v sub pi of I towards v sub pi of I plus 1 for every I running from 1 through n minus 1 will be simply half to the power n minus 1. Okay, so in other words, if x sub pi is the indicated random variable for the event that the directed graph, which is induced by our random tournament on the sequence v sub pi of 1, v sub pi of 2, so on up to v sub pi of n, gives you a Hamiltonian path. Indicated random variable, what does it mean? We have talked about this in the previous lecture video as well. It means that x sub pi takes the value 1 if the induced subgraph on the sequence, or rather, what I want to say is that when you look at the edges that go from v sub pi of 1 to v sub pi of 2, v sub pi of 2 to v sub pi of 3, and so on, this forms a Hamiltonian path. Then x sub pi takes the value 1. If it doesn't form a Hamiltonian path, then it takes the value 0. So using independence, as I said previously, the probability that x sub pi is equal to 1 is simply half whole to the power n minus 1, which is 2 to the power minus n plus 1. So how many such permutations are there? So we were fixing a permutation pi in the previous slide. How many such permutations are there? There are n labeled vertices, consequently n factorial such permutations. So now let's say that capital X is the random variable which denotes the total number of Hamiltonian paths that we obtain in our random tournament. Okay, because the tournament is random, therefore capital X has to be a random variable when you're counting the total number of Hamiltonian paths. And so what would capital X simply be? It would simply be the following summation. It would be summation of x sub pi, where pi is any, where the summation runs over all permutations pi of 1 through n, right? Because x sub pi is equal to 1 if the sequence defined by pi actually forms a Hamiltonian path. Sequence of vertices defined by pi actually forms a Hamiltonian path, and it is 0 if it doesn't form a Hamiltonian path. So when you add those x sub pi's which take value 1, you get the total number of Hamiltonian paths in the random tournament. So this relation should be immediate for you. And now notice that although we maintained independence while assigning the directed edges between the pairs of vertices in the graph, x sub pi's are not independent of one another. Okay, they're highly dependent. So for example, if you have 4 vertices, if n is equal to 4 for you, and you consider the permutations, let's say 1, 2, 3, 4, and 1, 2, 4, 3, then notice that in the first permutation, for the first permutation to be a Hamiltonian path, you require a directed edge from v1 through to v2. Similarly, in the second permutation, if that you require to be a Hamiltonian path, then you need an edge from v1 to v2. So these two things are not independent of one another. On the other hand, notice that for the first sequence to give you a Hamiltonian path, you need an edge from v3 towards v4, whereas for the second one, which is 1, 2, 4, 3, for this to yield a Hamiltonian path, you need a directed edge from v4 towards v3. These two cannot simultaneously happen. So this again shows you that these two, so x sub pi 1 and x sub pi 2, if you call these pi 1 and pi 2, these are not independent of one another, they're highly dependent. Okay, but we don't care about the joint distribution when we are talking about expectations. Again, so linearity of expectation comes to our rescue, and we can say expectation of capital X is, you take the summation outside, sum over all possible permutations pi of 1 through n, expectation of x sub pi. What is expectation of x sub pi? It's simply probability that x sub pi takes the value 1, which is, we have already found, is 2 to the power minus n plus 1. Okay, and so you get n factorial, because that's the total number of summons in this sum, times 2 to the power minus n plus 1. So since expectation of x is equal to n factorial times 2 to the power minus n plus 1, so from what we saw in the very first slide, let me just go back from this point, this last point in the very first slide, we conclude that capital X must assume some value which is greater than or equal to n factorial times 2 to the power minus n plus 1 with positive probability.
And this, what does this mean? So again, if an event happens with positive probability, it simply means that the event cannot be the null set or the empty set, which means in this particular case, so this is where we draw the conclusion from our probabilistic proof. We come back to our non-probabilistic setting. So because this particular event has positive probability, it tells us that there is a way of creating a tournament on n labeled vertices such that the total number of Hamiltonian paths that are obtained from the tournament is at least n factorial times 2 to the power minus n plus 1, which proves our claim. To give you an idea about how large this quantity is, n factorial times 2 to the power minus n plus 1, let me just show you here, because asymptotics plays another very big role in the kind of research that I do, which involves probabilistic methods, understanding of random graphs and their behaviors. So a lot of the time it's all asymptotically true. So what we have seen so far is, of course, it's true for all n, but we can try to understand what the magnitude of this number is like when you consider very large n. And for that, you can make use of Starling's approximation. If you're not aware of Starling's approximation, please look it up. I will try to make a video solely on Starling's approximation and its proof. It's a very nice approximation. So let me first say that this symbol, what this means is as follows. So when you write f of n, this curly symbol, g of n, for two functions f and g, that simply means that when you look at the ratio f of n over g of n, this ratio goes to 1 as n goes to infinity, okay? So in this particular case, this means that n factorial over this entire quantity will go towards 1 as n goes to infinity. And Starling's approximation is particularly efficient because even for pretty, relatively small values of n, this ratio is very close to 1, okay? So it's a very good approximation. So we can plug that in, and that gives us this quantity is roughly, so this 2 to the power minus n plus 1, this 2 to the power plus 1 comes outside as just a factor of 2. Then you have square root 2 pi n from here. And then finally here, you group together the terms that have n as their exponent. So here you have n over e whole to the power n times 2 to the power minus n, which simply gives you n over 2 e whole to the power n. And notice that this is increasing even faster than exponential because you have an n to the power n here, okay? So this is a very rapidly increasing function as n goes towards infinity. So it's a very, very large number when n is large. Okay, so let me move on to the second application. We will see 3 applications in total. So this is the second one, and this one is about bipartite subgraphs. Let me first and foremost say that I'm not sure if all of you know the difference between an induced subgraph and just a subgraph of a graph. So let's say that G is an undirected graph. So I mentioned undirected because so far we have been talking about directed graphs, but in the remaining part of the talk, we will just talk about undirected graphs and not directed ones. So let's say that the vertex set of G is indicated by capital V and the edge set by capital E. And the vertex set contains n vertices and the edge set capital E contains small e number of edges, okay? When you consider a subgraph capital H of G, if it is simply a subgraph, then the following is allowed. Let's say that U and V are 2 vertices of capital G that are also vertices in capital H. And let's say that in capital G, U and V are adjacent. If capital H is not an induced subgraph of capital G, then U and V are allowed to be non-adjacent in capital H. Okay? But if it is an induced subgraph, then if U and V are adjacent in capital G, they must be adjacent in capital H as well. Okay, so for example, when you consider a complete graph, any subgraph, any induced subgraph of it is also a complete graph. But any subgraph of it need not be a complete graph, okay? So this is what the difference is between induced and just ordinary subgraphs. And since I haven't really drawn and illustrated this, I'm just saying this out loud. So if you have any confusion again, please feel free to look it up on the internet. You should be able to see like pictorial representations of what an induced subgraph of a graph looks like, and what an ordinary, not necessarily induced subgraph of a graph looks like. Okay, so induced subgraphs are subgraphs, but not all subgraphs are induced subgraphs. And also, if you fix the set of vertices on which your subgraph capital H is based, then the number of edges that capital H would have if it is an induced subgraph is usually at least as large as, could be also strictly larger than, the number of edges that capital H would have if capital H is not an induced subgraph. Okay. So the claim here is that G, this graph is an undirected graph with n vertices and e edges. Nothing is specified, no properties required. So this is a pretty general result in that sense. So the claim is that G contains a bipartite subgraph with at least e over too many edges. Okay, so the caveat here is that we are not claiming that this subgraph is an induced subgraph. Okay. What does a bipartite subgraph mean? It means that G contains some subgraph capital H in which you can partition the vertices of capital H into two disjoint parts, capital A and capital B, such that any edge which is present in H goes between A and B. Okay, so there are no edges in capital H that are between vertices that both of which belong to capital A or both of which belong to capital B. Such edges are not allowed. Only those edges are allowed for which one endpoint is in capital A and the other endpoint is in capital B. So most of you already know what bipartite graphs look like, but in case you do not, this is what it means. And again, since I'm saying this rather than being able to illustrate, one of these days I really have to get a tablet. So anyway, since I'm not able to draw here, in case you need further illustrations, just Google this and you will be able to see some pictorial representations of bipartite graphs. Okay, so here is how we go about proving this. We will again use probabilistic method, and the way to do this is that you select a random subset of vertices, capital S, out of capital V. And the way you do it is something we already saw in the previous lecture. Every vertex small v in capital V is included in capital S with probability half and excluded with probability half. Okay, so you have a fair coin. You pick every vertex small v of capital V, you toss the coin. If it lands head, you include the vertex small v in capital S. If it lands tail, you throw out the vertex from capital S. You don't include it, okay? You exclude it. So this is also known as side percolation with probability half, something probably I mentioned in the last lecture. And you do this independently over all the vertices of capital V, okay? So you assume that all the coin tosses that you do, so for every vertex small v, you toss the coin once. So all these coin tosses are independent of one another. Now we will call, so keep in mind that capital G is a graph which is already given to you. So its edges are fixed, okay? You're not messing up with the edges. You're simply selecting a random subset of vertices. So now we will call an edge xy. So I write this with curly braces to indicate that this is not a directed edge. This is an undirected edge. And again, remember, this edge is already present in the graph. You're not adding this edge or anything like that. So for every such edge, for every edge which is already there in the graph, in the original graph G, you implement the following definition. You call that edge xy between vertices x and y crossing if exactly one of the endpoints x and y is in S, the other one is outside of S. Okay, so either x is in S, y is not in S, or y is in S and x is not in S. If both of them are in S, or if both of them are in S complement, then you do not call that edge crossing. Another thing that we will do is we will define delta of S, which is a pretty standard notation that is used to indicate the boundary of a set in a graph. So delta of S comprises all those vertices that are not in S, so V minus S, okay, that are not in S, but that have at least one neighbor in capital S, okay? So delta of S comprises all those vertices that are outside of capital S, but there is at least one vertex in capital S with which they're adjacent, okay? So this shows us that if you consider
the vertices that are in S union delta S, and you look at this set, and then your partition is S on one side, delta S on the other side, then we see that, first of all, they're disjoint because, as I say, delta S is a subset of V minus S. Okay, so these are disjoint, so they form a partition of S union delta S, and crossing edges are precisely those that go from some vertex in capital S to some vertex in delta capital S. Okay, so if you just look at this vertex set, S union delta S, and the partition is S on one side, delta S on the other, and the edges you consider are simply the crossing edges, then this will give you a bipartite subgraph. But keep in mind that this is not an induced subgraph necessarily, because in the original graph, capital G, you could have edges that are between vertices that are both in capital S, or you could have edges that are between vertices that are both in delta capital S. But those we are not including in this particular subgraph. Okay, so that's why this is a bipartite subgraph, but not necessarily a bipartite induced subgraph. Okay, so all we now need to show is that there is a realization of this random subset capital S, for which this particular bipartite subgraph has at least E over too many crossing edges. And this is how we go about it. So now comes so we have already incorporated the probability, but now comes the computation. So take any pair of vertices X and Y in the original graph capital G such that X and Y are adjacent in the original graph capital G. In other words, XY is an edge in capital E. Okay, let capital X sub XY denote the indicator random variable for the event that XY is a crossing edge. Okay, so capital X sub XY takes the value 1 if XY is a crossing edge. It takes the value 0 otherwise. So the probability that capital X sub XY is equal to 1 is what? So basically you look at the union of two events here. One is where small x is in capital X, small y is not in capital S. The other is where small x is not in capital S, small y is in capital S. But these two events are disjoint from one another. So you can, when computing the probability of their union, you can write that as the sum of their individual probabilities. So that is precisely what I have written here. And what is the probability that X is in capital S? That's half. The probability that Y is not in capital S is also half. And remember, the way we created the random subset capital S is by choosing which vertex belongs to capital S and which vertex doesn't belong to capital S. All these are happening independently over all the vertices. Therefore, this half gets multiplied with this half and you get a 1/4. Similarly, the probability that X does not belong to capital S is half. Y belongs to capital S is also half. So the probability that these two happen together is half times half, 1/4. So 1/4 plus 1/4 yields half. So the probability that this particular edge is a crossing edge is equal to half. Now let capital X denote the total number of crossing edges. Because capital S is a random subset, so of course capital X will have to be a random variable. And once again, you can write capital X as summation of capital X sub XY, where the summation runs over all the edges XY in capital E. Okay, so this is easy to see. Again, we are making use of the fact that each of these random variables is an indicator random variable. Okay, so now again, capital X sub XY, these are highly dependent random variables, most likely. Okay, so we don't know what the joint distribution is. It could be something very complicated. So for example, let's say you consider, let's say V1 is adjacent to V2 and V1 is also adjacent to V3. The event that the edge between V1 and V2 is a crossing edge is not independent of the event that the edge between V1 and V3 is a crossing edge, because both of them depend on whether V1 is in capital S or V1 is in capital S complement. So there are all these interactions that are happening. So these random variables together probably end up having a very complicated joint distribution, but we don't care because we have linearity of expectation to help us out. So that's why expectation of capital X you can write as sum of expectation of capital X sub XY, where the sum runs over all edges XY in capital E. Now, expectation of capital X sub xy is simply probability that capital X sub xy is equal to 1, which is half. And the total number of summands in this sum is E, small e. That's why you finally get small e over 2. And now this tells us, since expectation of capital X is equal to small e over 2, so there is some value which is less than, greater than or equal to small e over 2, that capital X assumes with positive probability, which means now we go from probabilistic to non-probabilistic interpretation. So since this happens with positive probability, so we can say that this is not an empty set, which indicates that there is some choice of capital S for which the number of crossing edges is going to be at least E over 2. And that leads us to the final conclusion that we desired. Okay. This is a small exercise that I incorporated. It just gives you a slightly improved estimate is all. So here, let's say capital G has an even number of vertices, okay, 2 and many vertices. And you're choosing capital S, but no longer in the manner that we chose in the proof that we just saw just now. Here you're choosing capital S uniformly randomly out of all possible n element subsets of the vertex set of capital G. Okay, so there are 2 and many vertices. There are 2 and choose n many ways of choosing subsets of vertices that have cardinality n. You choose capital S uniformly randomly out of this entire collection of n element subsets. And uniformly randomly simply means that each of these n element subsets has equal probability of being equal to capital S. Okay? So now under this probability measure, calculate the expected number of crossing edges, and then you can draw the final conclusion exactly as we saw in the proof before. Okay, so all you will see is that here you have here the bound that you got, the lower bound that you got is E over 2, so half the total number of edges. There you will see it's slightly better than half. That's all. The final application is to edge colorings of graphs. Okay, so edge colorings of graphs are something that we saw in the last lecture, or basically the first lecture, when we were studying Ramsey numbers. Okay, so when we tried to get lower bounds on Ramsey numbers. So once again, recall that this is a standard notation. K sub n is the undirected complete graph. Again, I'm specifying it's undirected because we talked about directed graphs at the beginning of this presentation. And so K sub n is the undirected complete graph on n labeled vertices. And the two coloring is basically an assignment of colors blue and red to the edges of the graph. So you pick each edge of the graph and you color it either red or blue. Claim is there is a two coloring of the edges of K sub n such that it allows at most these many monochromatic K sub a. A here is some positive integer which is less than or equal to n. Okay, so n choose a 2 to the power 1 minus a choose 2 is the maximum number of monochromatic K sub a's that are allowed. Such a two coloring exists is what you have to prove. So once again, we bring in probability. We start off with a random two coloring of the graph. So to each edge of K sub n, you either assign the color blue with probability half or red with probability half, and you do this independently over all the edges of K sub n. Okay, so the idea is you're probably pretty familiar by now with this idea. This is the idea we also made use of when finding lower bounds on the Ramsey numbers. Now, you consider any subset capital S of the vertices of capital K sub n, such that capital S is cardinality A. So the induced subgraph on capital S is going to be K sub A, right? Because K sub n is a complete graph, so any induced subgraph will be another complete graph. What is the chance that this induced subgraph will be monochromatic? What is the chance that this is going to be blue entirely? It means that every one of the edges inside the induced subgraph on capital S has to be blue. Okay, how many edges are there like that? A choose 2 because you have totally a number of vertices in capital S, and so the complete graph on capital S will have A choose 2 many edges. Each of them has probability half of being blue, and this is happening independently over all the edges. So therefore, the probability that capital S is full, the induced subgraph on capital S is fully blue is half to the power A choose 2. Similarly, the probability that the induced subgraph on capital S is fully red is also half
whole to the power a choose 2. Therefore, the probability that it is monochromatic is twice half whole to the power a choose 2, which is 2 to the power 1 minus a choose 2. Okay. We can also do this using indicated random variables. So let's say capital X sub capital S is the indicated random variable for the event that the induced subgraph on capital S is monochromatic. Then the probability that capital X sub S takes the value 1 is simply this quantity, 2 to the power 1 minus a choose 2. Okay. So capital X, let capital X be the total number of monochromatic K sub A copies that are inside K sub N under this random coloring. So because the coloring is random, capital X is also random. Okay, so capital X counts the total number of copies of K sub A inside K sub N, which are all monochromatic. Okay. So then once again, we can write capital X as sum of capital X sub S, where the sum runs over all subsets S of the vertex set of capital K sub N, such that S has cardinality A. Okay, that's again follows from the fact that these are indicated random variables. Again, these X sub S's they will be very highly dependent on one another because some of them will have like big overlaps, and for those, there will be a lot of dependence, a lot of correlation. But again, expectation has this linearity property, so we don't care. So we can write expectation of capital X is sum expectation of capital X sub S, where the sum again runs over all subsets S of the vertex set with cardinality A. Each expectation of X sub S is equal to this quantity, right? 2 to the power 1 minus a choose 2, because expectation of X sub S is probability of X sub S equal to 1. So 2 to the power 1 minus a choose 2 is what we get for each summand. And how many summands are there? There are n choose a many summands because there are n choose a many ways of selecting a subset of A vertices out of a set of n labeled vertices. Okay, so since expectation of X is equal to this particular quantity, therefore you can say that X must assume some value which is less than equal to this quantity with positive probability, which means, again, because it's happening with positive probability, that there is a way of assigning two coloring to the edges of K sub N such that there are at most these many monochromatic K sub A's. Okay, so hopefully this was helpful, and hopefully I'll continue to make videos like this. Feel free to leave some comments if you have questions. Also feel free to leave those questions underneath the YouTube video. Yeah, so I guess I'll stop here. Thank you so much for listening.